Hi again. This is the second video of the review that's in chapters 2 and 3 of probability and statistics. And when we ended the last video, the first part of this, we were talking about bivariate or multivariate joint. They're also called distributions. And we said we can denote that as f of x, y, of x and y. It's the notation we use. And again, so we talked about, suppose that you had an experiment where you had a spinner and it had 1, 2, 3, 4 on it were the only outcomes. You spin it once, spin it twice. X could be the number of ones in those two rolls. Y could be the number of fours. Or you could roll 2 dice and X could be the number of ones, Y could be the number of sixes, something like that. This f xy of xy is the probability of x and y happening, so the probability of x equals 1, y equals 6, something like that. Then we talked about marginal distributions, and we said that the distribution of x can be obtained from the joint distribution, and what you do is you sum over y of the f xy of x and y, and we did an example of that. So if you're not sure about this, go back and look at the example at the end of the last video. And we also said you can find fy of y in the same way. You sum over x of the f x y, x and y. These were the discrete cases. I think I forgot to write down the continuous, so let me do that. So if this distribution is discrete, this is how you would do it. If it's continuous, then f x of x would be the equivalent of a sum in continuous space, which is an integral, over, again, the distribution f of xy of x and y, and this time dy. That's the equivalent to summing over y. So it's the same sort of thing. You're summing over y to get the distribution of x. And again, if you're not getting the intuition on that, go back and look at the discrete case. This is just the continuous time analogy to the discrete case. Similarly, fy of y would be the integral from minus infinity to infinity of the joint distribution. But this time what we do is we sum in the x direction. We sum across the x's. Just like here, when we get fy of I, we sum over the x's. Here we sum over the x's as well. And so I left that out of the last time. And so I wanted to make sure that I wrote down the continuous time formulas for that. Okay, now, there's an important way in which the marginal distributions are related to the joint distribution. So let me give you that. So this is a definition of independence. So we can use this stuff to define when random variables are independent. That's going to be very important when we do regression models. We're going to make an assumption, for instance, that the error terms are independently and identically distributed. So we're going to make an assumption that each error in our model is independent of the other errors. When that assumption is violated, it causes all sorts of problems in our regression models, and then you have to fix it. And so this notion of independence, statistical independence, is very important in regressions. So how do we define it? Okay, so the random variables, x and y, are said to be independent if, and this is not an if and only if, this is just an if the joint distribution is the product of the marginals. And that's an important relationship again. So when this is true, you have independence. When it's not true, then you don't have independence. And in a few minutes, maybe I'll do an example of that. for now, let's just move on to mathematical expectations. So this is a definition of statistical independence. If the joint is the product of the marginals. If this was f, x, y, and z of x, y, and z, we'd have an f of z on here again. It'd be the product of all the marginals gets the joint. So we can extend that to more than two variables as well. So that's independence. Okay. Mathematical expectations. Just like in the univariate case, in the one variable case, I'm trying to write here, mathematical expectations. So we can define expected values similarly to what we did for the univariate. So the expected value of x to the r. So this is the rth moment. The expected, when r is 1, you get the mean. When r is 2, that's the expected value of x squared. There's an easy way to turn that into a variance. So the second moment's essentially a way to get at the variance. Remember that? And then there's higher moments that have meanings. This is just, in the continuous case, it's a double integral for a bivariate case. So we integrate over both x and y. And it's just x to the r power times fxy of x and y dx dy. So it's just like with a univariate, except we have to sum over both variables. So it's just the outcomes times the probabilities. The outcomes the r power times the probability. If it's discrete, it's the sum over the x outcomes, the sum over the y outcomes of x to the r f x y x and y. So the mean, the expected value of x would just be x to the 1. It would just be the sum of the x times the probabilities. We called this pi when we did this earlier, but this is the same thing. Those are just the probabilities of each outcome. Okay? Now you can also find what's called the joint moment. Though it's not used as much as the others. But you can also define the expected value of xr, x to the s. That's a joint moment. This should have been a y. And again, it depends upon whether it's discrete or continuous. If it's continuous, it's a double integral. You can probably guess what this is going to be. Instead of x to the r, it'll be x to the r, y to the s, f x y, x and y, dx dy. Or it's the sum over the, which one I do first here, x's, the sum over the y's, x to the r, y to the s, f x y, x and y, if it's discrete. And that's called the joint moment. Again, we don't use that much. Except when there is one case when x is 1 and y is 1. That basically is related to the covariance and the correlation. And so that's the one joint moment that we tend to use. So the most important joint moment is the covariance. Is defined as, we're going to write it as sigma x y. That's the covariance. Another way we'll write it is the covariance of x and y. These are equivalent notations. They're completely interchangeable. It's equal to the expected value of x minus the mean of x times y minus the mean of y, where u of x is just the expected value of x, just like we did earlier, and mu of y is the expected value of y. And this is called the covariance. In the continuous case, for instance, it'd be the integral minus infinity to infinity, integral minus infinity to infinity of x minus mu of x, y minus mu of y, f x y of x and y dx, dy. So it's just what you'd expect for an expected value. So that's this expectation. That's the covariance. All three of those things are identical in terms of what they mean. Now, the covariance could be positive or negative, depending. Let's think about that. If it's positive, what does that mean? It means that when x is above its mean, y is likely to be above its mean, so that both of these are positive. So that whenever x tends to rise above its average value, y tends to rise above its average value. They covary positively. They move in the same direction. When x is below its mean, that's negative. And if y tends to be below its mean at the same time, then you would expect to see, again, a negative times a negative would be a positive covariance. So if x and y are positively related, you tend to see, when x and y move in the same directions on average, you see a positive covariance. For instance, you might, I think this would be true, height and weight are probably positively, probably have a positive covariance. Because if someone's tends to be above the average height, they probably also tend to be above the average weight just because they're taller. So you'd get a positive covariance in that case. If the opposite's true, if whatever x is above its mean, y tends to be below its mean, or this is below, this is above, then that's always negative, and the covariance is going to be negative. So in that case, we have a negative correlation. You could draw this, for instance. Say you had a positive covariance. Here's y, here's x, here's y bar, and here's x bar. If you have positive correlation, whenever x tends to be up here, y tends to be up here too. When x tends to be down here, y tends to be below its mean. So the points would be scattered like that for a positive correlation. For a negative correlation, they'd go in exactly the other direction. So whenever x is above its mean, y tends to be. Now, it might not always be. There might be occasions where it's not true. But for the most part, on average, when x is above its mean, y is above this. Remember, this means on average. Do you see that E thing? What we're saying is on average. On average, when x is above this, y is above this, is what that would mean. So that's the covariance. It just tells us the relationship between two variables. There's also something called the correlation coefficient. So it's usually written as rho of x and y. And it's the covariance of x and y over, how did I write it here? The standard deviation, sigma x, sigma y. Sometimes this will be written as, remember, that's another symbol, sigma xy over sigma x, sigma y. This is another way to write the covariance. And so it's just the covariance over the product of the standard deviations of x and the standard deviation of y. And that's called the correlation coefficient. It's always between 0 and 1. 1 is perfectly negative correlated. 1 is perfectly positively correlated. And rho equals 0 means there's no correlation at all. So if rho is 0, and you have x here, y here, and here's x bar, here's y bar, there's no relationship between, if the correlation is 0, there's no relationship. It's just a scatter of points. When x is above its mean, y is above or below. You can't really tell. When x is below its mean, y is above or below. You can't really tell. And so the correlation would be 0. The closer you get to, say you have x bar and y bar, and then it's not perfect, but boy, they're pretty close to a straight line. That's when this is a positive. That rho would be getting closer to 1. So the more these things tend to organize into a straight line, if it was a perfectly straight line, you had perfect correlation, one's always above when the other is, then the correlation would be 1. And so the correlation coefficient's between -1 and 1, and it tells you the strength of the correlation between the two variables. The other thing useful about the correlation coefficient is that it is always, it's unit free. And so if I take x and y, and x is measured in inches, and I change that into feet, or go the other way, it's in feet, and I change it to inches, it doesn't change the value of the correlation coefficient at all. The covariance would change. And so, so you can tell whether things are positively or negatively correlated with the covariance, but its magnitude, how big it is not very informative, because I can make it as big as I want just by changing the units that I'm measuring in. I could go to 1/10 of an inches, or I could measure in yards, I could measure in miles. Depending on what unit of measurement I choose for x or y would change the covariance to whatever number I wanted to get. So it's not telling me very much about the strength of the correlation. The correlation itself, though, this thing, as opposed to the covariance, is unit free. And so it's always between -1 and 1. And so its big advantage over the covariance is it gives you information about how strong the association between x and y is. As it gets closer to -1 or 1, you get closer to perfect or positive or perfectly negative correlation. All right. Now, one thing that we can say then is we can go back to our definition of independence. We know if something's independent, it means f of xy equals fx times fy, what we did a few moments ago. There's something else, too, here. If x and y are independent, then the covariance, let me write it this way, sigma xy, the covariance, is equal to the correlation and 0. And so it's always the case that if they're independent, then this is true. The converse is not always true. You can have a case where it's possible that sigma xy equals rho xy equals 0, but x and y are dependent. So if it's independent, we know the covariance and the correlation are 0, but just because we observe a 0 correlation doesn't necessarily mean the two variables are independent. And I'm trying to think if I need to do an example of that. Your book doesn't do an example of that particular thing. So maybe I will skip that and leave it to the statistics courses to show that. But I do have an example. Why not? So in this example, y can take on 3 values, 6, 8, and 10. So that's y. X can take on the values 1, 2, and 3. And the probabilities are 1/5. So that's the probability that x equals 1 and y equals 6. 0, 1/5. This one is 0, 1/5, 0. And this is 1/5, 0, 1/5. There's 5 of these. So the probabilities sum to 1. And so there you have it. Now you look at the marginals. So this is fx of x. Inside here is fxy of x and y. And over here is fy and y. Remember, the way you get the marginal for y is you sum over the x values. So this is 2/5, 1/5, and 2/5. And these have to sum to 1, and they do. This one's 2/5, 1/5, and 2/5. So we can see easily that these two things are not independent. Why? Remember, if they're independent, means that fxy of x and y is fxx times fy and y. And just look at any value here. Take this one. 1/5 times 2/5 is not 0. 2/5 times 2/5 is not 1/5. So I can't get the joint by multiplying the marginals together, which is what this says I have to be able to do. So it's just not the case that this one is equal to that times that. Okay? So these are not independent. They're not independent. But I'm going to have to erase, I'm sorry. In this thing, if you look at the expected value of x, it's equal to 2. The expected value of y is equal to 8. And the expected value of xy is equal to 16. And there's a formula that says the covariance of x and y, what we've been calling sigma xy, is equal to the expected value of x and y minus the expected value of x, expected value of y. And that's something you should have learned in your statistics classes, probability classes. So this is just a formula you can use to find this. And it's pretty easy to show this is true. You take the expected value of x minus u of x, y minus u of y, the original definition. You multiply it out, some things cancel, and you're left with this. So in this case, the expected value of xy is 16 minus 2 times 8. So that's 16 minus 16 equals 0. So the covariance is 0. But we know they're not independent because the product of the marginals didn't meet the joint. So this is a case where we have a 0 covariance, but we don't have independence. The other way is always true. Independence always gives you a 0 covariance, but a 0 covariance or a 0 correlation does not always give you independence. By the way, do you know how to, let me go back and do something here. Let me put the numbers up again. I'm going to show you where these came from, just in case you're not sure of that. So y was 6, 8, 10. These were the y values. X values were 1, 2, and 3. Those were the x's. And this was 1/5, 0, 1/5. Down bottom was the same, 1/5, 0, 1/5. And the middle was the opposite. And then we had the marginals, fy of y, were 2/5, 1/5, and 2/5. And the marginal for x was the same, 2/5, 1/5, and 2/5, because this thing's symmetric. Now, how do you get the expected value of x? Well, the expected value of x is just the probability of x times the value. So what's the probability that x equals 1? Well, the probability that x equals 1 is 2/5. It's this plus this. Well, I don't care what the y values are. The probability that x equals 1 is 2/5. So to get the expected value of x, what we do is we take the sum of the probabilities times the outcome. So that the outcome is 1 and the value is 2/5. What's the probability that x equals 2? Well, it's 2 times 1/5. And what's the probability that x equals 3? Well, it's 3 times 2/5, right? Because if we add these up, that's the for x equals 3, there's two ways it can happen. The 1/5 of the time is when this happens, and 1/5 it's across all the y's, the probability that x equals 3 is 2/5. So what is this? This is 2/5 plus 2/5 plus 6/5, which is equal to what? 10/5, which is equal to 2. To get the expected value of y, what would I do? I would take 2/5. There's two ways it could be 6 when x equals 1, x equals 3. So it's 2/5 times 6 plus 1/5 times 8 plus 2/5 times 10. That's 20 plus 8. 20 plus 8 plus 12. Did I do that right? Yeah. And then you'll get the right value there. And so in this case, the expected, you can figure out what the expected values are. Okay. So let's go on. Okay, that's right. Okay. I was thinking the expected value of y was, I was doing something weird in my head. Yeah, that's right. You get 2/5 times 10 is 20/5, plus 8 times 1/5 gives you 8/5, so that's 28. And you get plus 12, which is 40/5, and 40/5 is 8. Yeah, it works out. So again, you just take the sum of the y outcomes times their probabilities. And there you have it. All right. And to get this one, how do you get this one? You would take, it's the expected value of xy. So you take x times y. So it's 6 times 1/5 plus that times that, 8 times 0 plus 10 times 1/5, that's the first row, plus 12 xy, that's xy, it's expected value of x times y, so x times y is 12, times the probability is 0, plus 16 times 1/5 plus 0, the probability is 0, this times this is 20 times 0, plus 3 times 6 is 18 times, there should have been a plus sign there, 18 times 1/5 plus 3 times 8 is 24 times 0 plus 3 times 10 is 30 times 1/5. So this is the expected value of xy. X times y. You just take x times y times the probability, x times y times the probability, x times y times the probability, add them all up. That's how you get this number. And if I add all these up, how many fifths do I have? I have 6 plus 10 plus 16 plus 18 plus 30. And that's equal to 32 plus 48, which is 80 over 5, and that's equal to 16. So that's where this number comes from. It's just the expected value of xy. So you see how to do these expectations? The expected value of something in these discrete things is just, you just take whatever it is times whatever it is. If this was x squared y, if we were looking at the second moment, x squared y squared, it'd be 1 times 36 times this. It'd be 4 times 64 times this, and so on. Okay, well, if you don't have that down, I encourage you to go look at the book's examples of those sorts of things and see if you can get it straightened out. Or rewatch the video and hope the second time through it makes a little more sense for you. Okay. So here's some other things that are useful to know about joint distributions. We've already talked about this one. So that's the first property that's useful for joint distributions. For the second property is that the variance of ax plus by, where x and y are random variables, and these are just coefficients, these are just numbers, a and b, is equal to a squared times the variance of x plus b squared times the variance of y plus 2 times the covariance of x and y. Oh, 2ab plus 2ab times the covariance of x and y. If they're independent, then it's equal to a squared times the variance of x plus b squared times the variance of y. And that's because the covariance, if they're independent, would be 0. And you can extend all of these things to more than one variable, but I'm not going to do it. I could have a variance of ax plus by plus cz, and then it's going to be a slightly more complicated formula, but it's just a generalization of what you're seeing here. Good enough. Okay, we're getting there. Getting on through the review here. 31 minutes so far. Okay, how much more do I have? Not that much. A little bit, quite a bit. Next, let's talk about some probability distributions, and I'm not going to spend a lot of time on this. This is not something your book spends much time on, and so I am not going to either. I might say a little bit more than the book says, but not a whole lot. The most common one we'll use is the normal. That's the one that looks like it's the bell-shaped curve, centered on the mean. Its formula we talked about earlier. If this is x, then the distribution of this f of x is equal to 1 over the standard deviation square root of 2 pi e to the minus x minus mu squared over 2 sigma squared. Often, we will want what they call a normal 0, 1. When we specify normal, all you need to know, the only thing you need to know is the mean and the variance. Once I know the mean and the variance, mu and sigma squared, I know the whole distribution. So we can characterize this with just 2 parameters. And often what you're interested in is a normal 0, 1. In that case, this is 1, this is 0, and you just get over 2. So in that case, this collapses to a slightly simple form. And this is called a standard normal. But a normal is just a bell-shaped curve. And we will use that extensively to do hypothesis testing. And we'll come back to this. And so we'll want to know what a 95% confidence interval looks like. Basically, it'll be plus or minus approximately mu. If this is 1.96, if this point is mu plus 1.96 times the standard error, and this point is mu minus 1.96 times the standard error, in between there is the 95% probability range. And that 95% probability range for x will be something that will be useful for us, and we'll come back to how that's useful. But so a normal distribution has this nice property that 95% of the area is always between the mean plus or minus 1.96 times the standard error. So usually you just write it as mu plus or minus 1.96 sigma. That's the 95% probability range for a normal random variable. And as I said, we'll use this quite extensively to do hypothesis testing later on. Another distribution that we'll use quite a bit, though not as much, is a chi-square. And it involves a gamma function, which you probably don't know much about. But let me put it this way. The sum of n independent normal 0, 1 random variables is distributed chi-squared with what we call n degrees of freedom. When you look up the probability ranges for a chi-square, it will depend upon these. So if I have 3 independent, normally distributed 0, 1 random variables, there's 3 of these, and I square them, x squared plus y squared plus z squared. All 3 of those are normal 0, 1s. That distribution will be a chi-square with 3 degrees of freedom. Now, where this is useful is often, well, when you calculate variances, you end up squaring things and summing things. And so when we calculate a variance, it'll basically be the sum of the x minus the estimated mean squared over n minus 1. That will give us a sum of n normally distributed random variables. And if we do a little transformation to make them normal 0, 1s, we can get a chi-square. And so because variances are sums of squares, and they're often based upon normals, the chi-square becomes very useful for testing hypotheses about a variance. So if you want to test that a variance equals a particular value, or it's bigger or less than a particular value, the variance is bigger than 10 or less than 10 or something like that, then these chi-squares turn out to be very, very useful. And I'm hoping you worked a little bit with these chi-squareds at some point. What they look like often is they're asymmetric. They sort of are hump-shaped like this. So a lot of the probability is in this range. Because they're squared, you're squaring random variables, you never get negatives. A variance can't be negative. And so the probability range is defined all in the positive space. And this peak point moves around depending on how many of these are. So the shape depends upon how many random variables that you add up. But, and in fact, if you let this number get very large of these n random variables you're adding up, this starts to look more and more like a normal. But that's not something we need to worry about. The next one we can talk about, so that's a chi-square. I guess I should have written it down. That's chi-square, so that this is this is the English way of writing it. Now the next thing is a t-distribution, and those are something that you should have seen a lot of when you were doing statistics. It looks like a normal, but it has fatter tails. There's more probability out in the tails than there is for a normal. So it looks just like a normal, but there's more probability out here in the tails than there are for a normal distribution. When n, the number of observations, goes to infinity, this t-distribution goes to a normal. And when n is greater than or equal, so say you have a data set of 30 or more, when n is greater than 30, you can be pretty sure that the normal approximation is pretty good. And so we will use a normal approximation almost always when we're doing our statistical tests, because in economics, n is almost always greater than 30. So we can almost always use the normal approximation of the t-distribution, and that's very, very handy and useful. And I'll cover that point in a lot more detail later. For instance, what you probably learned in your stat classes was that suppose I want to test that the mean of a distribution is equal to 10. And the alternative is that the mean is not equal to 10. The way you estimate the mean is with x bar. And so the t statistic that you learned was equal to x bar. This, in my example on the first video, I made this 12. This might be 12 minus 10 over the standard deviation of x bar, which turns out to be sigma squared, the variance of x over n. So if x is distributed normal, then x bar, the mean, is distributed normal with the same mean, and the variance is sigma squared over n. So this would be the sigma squared x over n. This is distributed normal 0, 1. By subtracting off the mean, if the null is true, if that's the true mean, this transformation gives you a normal 0, 1, and you can use that to do test statistics. So you can just look up a normal distribution in the back of the book and use the normal probability values to figure out whether to accept or reject an hypothesis. We'll go through a lot of that later. I don't want to do hypothesis testing right now. The thing is, though, if sigma x bar is not known, which is the usual case, and we replace it with our estimate, and we use t equals x bar minus 10 over s of x bar, that's the estimated value. And we'll talk about how to do these estimates later. So we don't actually know this. Then this is distributed t. And the degrees of freedom are n minus 1. If the number in your sample that, so you're calculating the mean, you've got 100 x's. So you've got 100 x's. Then x bar is just the sum of those x's over 100. That's the average value. You learn how to do that. Then this would be t of 99. It'd be 99 degrees of freedom. So this is t with n minus 1 degrees of freedom. And we could prove all this. I'm not going to do it. And so that's when you'd want to use a t distribution. But as long as n is greater than or equal to something around 30, that t is so close to a normal that we may as well use a normal. And so t infinity, if I have an infinite number of observations, is the same as a normal distribution. But most of the time, we won't bother with a t table at all. We'll have n greater than 30, so we'll use normals instead of t's. But the t statistic is going to be this thing. The estimated value minus the hypothesized value over the standard error of the estimate, whatever it might be. That formula is always the same for a t. And as I said, we can usually use the normal approximation to do hypothesis tests, and we'll come back to that. The final distribution that we'll be interested in, and this one we'll use quite a bit as well. We'll use the normal and this one the most, I think. We'll use a lot of t statistics, but we'll use the normal distribution, is an f distribution. And it looks kind of like a chi-square. Depending upon the degrees of freedom, it looks sort of like this. Depends on the particular degrees of freedom. I'll talk about that in a second. If x and z are independent and distributed chi-square with n1, n1 is for x, you might call that nx, and n2 degrees of freedom. x over n1 divided by y over n2, x over its degrees of freedom, y over its degrees of freedom, is distributed f with n1 and n2 degrees of freedom. When you look at an F table, there's a separate table for every n1 and every n2 combination. And so the value of an F distribution depends upon n1 and n2. And remember, n1 and n2, these are chi-square. The chi-square is the sum of normals. So if you summed up n1 normals, you'll get x. You sum up n2 normals, you'll get y. And then this is how you get an F. This is useful for, say we have two different variances. Say we run regression on half the sample, and we get sigma squared 1, an estimate of that, s squared 1. And we have another estimate from the other part of the sample, s squared 2. I can test whether these two variances are equal using something like this. See, what happens is, if they're equal, what's going to happen? I have to divide by my degrees of freedom over n1 and over n2 is what you end up doing. But essentially what the intuition for the F statistic is, suppose I want to test if these two things are equal, then if they are equal, this will be 1. So if the value of the statistic is 1, it's very likely that they're the same. As you always put the bigger one on top just by convention. As this gets bigger and bigger relative to this, this is the F statistic. The F stat gets bigger and bigger and bigger and bigger. And at some point, you want to say, well, when does that difference in the two get so large that I'm willing to say these are not the same? And that's what the F distribution tells us. At some point, you can look up in the table, there's a critical F that if you get a value of this ratio that's bigger than that number, you're going to say they're not the same. If you get a value that's less than that, you're going to say it is the same. I mean, this is how you do all statistics. You find something that as the null gets more and more true, the number's small. And as you get further and further from the null being true, the thing gets bigger and bigger. And at some point, and the distributions tell you that, you say, oh, it's too big, and we're going to cut it off. For instance, for the T distribution, let me go back to the T statistic. Remember, the T was x bar minus the hypothesized value over the standard error of x bar. When these things are close together, this is a really small number. And you say, oh, it's probably true. As it looks, we're just taking a sample and calculating this. These aren't necessarily going to be equal, but when they get far enough apart, we're going to say, oh, those aren't equal after all. It doesn't look like they're equal. The data is the measured mean is so far from the hypothesis one, the hypothesized value, that we don't think it's true. So what happens is as your estimate gets further and further from the hypothesized value, this gets to be a bigger and bigger and bigger number. And when you get to a particular level, which turns out to be 1.96, that 1.96 again, if this is greater than 1.96, we say, oh, that's so big that we don't think this is true. What that means is you're more than, let's just round 1.96 to 2. You're more than 2 standard deviations from the hypothesized value. And when you get that far away, then we're going to say, oh, this hypothesis isn't true. So we're trying to find a way to avoid our own biases entering into this. So we have an hypothesis, and we want a way, and we want it to be true. You know, this is our dissertation or something, some paper you've been working on for 2 or 3 years, and you really, really, really need your hypothesis to be true. And so you run some statistical test, and it's kind of close. You're going to kind of fudge things and do other sorts of things to try to make it come true. I mean, that temptation would always be there to sort of find a way to make yourself believe, and that's just human, that this thing isn't true. So what statistics is trying to do is take that bias out. It's trying to find a systematic way to take an hypothesis. You're supposed to do the hypothesis before you ever look at the data. So you form your hypothesis. You then form your t-value, And then if it's greater than 1.96, you reject. If it's not greater than 1.96, you fail to reject. And if you do this honestly, you don't have any choice about that. You can't say, oh, it's close enough. I got 1.98. Therefore, oh, that's close enough. Let me go ahead with this. Now, there's a particular cutoff value, and you stick with it. So those are the main probability distributions that we're going to look at. The normal, which is often called a z statistic, the t statistic, the chi-squared statistic, and the f statistic. And those are the corresponding distributions. Okay, one last topic here, and then maybe, well, there's one tiny, tiny one at the end, but this is the sort of the last big thing for this review, and that's the properties of estimators. An estimator is just some function of the data. So if I want to estimate the mean, the thing I use is, and I have some population out there, and I draw from that population, and I draw x1 to xn. So these might be heights of people in the US, and I want to know what's the average height of people. So I pick 2,000 people and measure them, measure their heights. So n would be 2,000 or 100 or whatever it is. Then the estimate of the mean is 1 over n times the sum of the xi. So I just add up all the heights. You know, if there's 3 people in a room, 4, 5, and 6 feet, the average height is 4 plus 5 plus 6 over 3. It's 5, obviously. So use that formula. And that's what we mean by x bar. That's called the mean. That's an estimate of mu of x. This is the true population mean, the true mean of people all over the US, their average height. So every person in the US, every single one of them, if we added every one of them up and divided by n, that's not a statistic. That's the population mean. That's the true mean, because we have the entire population. What we're doing is taking a sample. Say, of 100 people. So we go out, we randomly pick 100 people in the US, and we measure their average height. We use that as an estimation of the population mean. Well, it's not going to necessarily be the same as the population mean. And so, this is an estimator. There's an estimator. Sigma squared is the true variance. S squared is the estimate of it. What it is the sum of the xi minus x bar over. It turns out you have to divide by n minus 1 for reasons we'll talk about later. That's called a degree of freedom correction. Because we calculated x bar, we lose 1 degree of freedom, so we have to divide by n minus 1. I'll come back to that later. So this is the way we estimate sigma squared is with this thing. And so these are just various ways of estimating the population parameters, the true mean and the true variance of height. This is the estimated mean and the estimated variance based upon a sample of 100 or 1,000 or 2,000 people or whatever we take. The bigger that sample is, the more precise we'll be, which is what this tells us. As n gets bigger, this tends to get smaller on average. But anyway, so what are some desirable properties of those estimators? The first one is a property called unbiasedness. Lack of bias. So an unbiased estimator what that means is that the expected value of the estimator is equal to the true. So this is maybe B is the mean. The expected value of the mean is equal to the actual value. For instance, what's the expected value of x bar? Well, that's the expected value of 1 over n times the sum from 1 to n of the xi. Turns out for expectations, I can pull it inside. That's 1 over n times the sum from 1 to n of the expected value of the xi's. Remember, the xi's are distributed normal with mean mu and variance sigma squared. They all have the same mean. They're identically distributed. The true mean of the population is the same. So when we draw it out, it's the same. So the expected value of any xi is just the mean. So this is 1 over n times the sum from 1 to n. The expected value of each x is mu, which is n mu over n, which is mu. So this is an unbiased estimator because when we take the expected value of the estimator, it's equal to the true value. So in pictures, what it means, think of we're measuring the height of people in the US, all the millions of people. And we draw a sample of 100 and we measure the height. We'll get some number, 5 feet 1 inch. We take another sample. We get a different mean. Maybe we get 4 feet 7. And we keep doing this. Each time we do it, we're going to get a different value. And so the estimator B hat has some distribution. And if it's unbiased, that distribution of beta hat will be right at beta. So for the mean, this is x bar. And it's unbiased if that mean is equal to mu. If it looks like this, here's the distribution of x bar in the population, and the true mean is out there, so the average value is something else, that would be biased. Because on average, x bar is not the true value. See, the idea here, again, remember that the expected value means on average. When you see that E, don't let it throw you. It means on average. So we're saying the expected value of x bar is equal to mu. On average, this is equal to mu. What that means is if I take a sample of 100, measure x bar. Another sample of 100, measure x bar. Another sample of 100, measure x bar. If I did that an infinite number of times and I averaged all those x bars, I'll get the true value. It's just like taking a larger sample, right? If I flip a coin 10 times and say on average, what did I get? It won't necessarily be a half. If it's 0 and 1, remember our 0, 1 example for heads and tails. On average, I won't necessarily get a half. I could get 8 heads and 2 tails. Then I do another sample of 10, and then I get 2 and 10. 2 heads, 10 tails, and I do another one, and I get 6, and another one, and I get 7, another one. If I do that an infinite number of times and I average all those means, I'll get the true value. On average, the mean would be correct. In any individual sample, it won't necessarily, but on average, the mean would equal the true value. And that's unbiasedness. Okay, the second property is efficiency. If I have 2 estimators of x bar, one with this distribution and one with this distribution, I didn't draw that very well. I want them both centered on the same value, and that's not so cool. Let's try that again. So I want a really narrow distribution, and I want a really flat one, and I want them both to be unbiased. So both of these are unbiased. But this one has a much smaller variance than this one. On average, this is a lot closer than this one. Which of those 2 estimators would I prefer? Well, I'd prefer this one because it's, in any given draw, it's likely to be closer to the truth. So the formal definition of efficiency is that Efficiency means the variance of beta hat is less than the variance of beta tilde. This is one estimator. This is another estimator. For the mean, I could also estimate the mean. You wouldn't want to do it this way, but I could just take the largest value and the smallest value and average those, right? That's an estimate of the mean. Turns out that's going to be unbiased if you were to work it out, because it'll be just expected value of x biggest plus x smallest over 2, and you'll get mu plus mu over 2, which is 2 mu over 2, and you get mu. Well, it's just a different estimator. But which one's better? Well, that one would have a bigger variance, it turns out, because that will just have more variation than averaging a whole bunch of numbers. So if this is true, where beta tilde is any other estimator of beta, then beta hat is efficient. It's the most efficient variable, the most efficient estimator. Anything else on efficiency? No. Let's move on from there. So unbiased means the estimator is centered on the truth. Efficiency means the estimator has the smallest variance among all estimators. Often we'll have a choice of estimators, all of which are unbiased. Which one should we use? Well, we want the one that's most efficient. Finally, there's something called consistency. And we're going to rely a lot on consistency. It's a nice property. And if you go on in econometrics, you'll see that the mathematics with this are much easier than with expectations. You can do things here, taking limits that you can't do with expectations. This looks at what looks at what happens, that's pretty sloppy, to the estimator as n goes to infinity. So for unbiasedness, our sample size n is fixed. And we're saying on average, would that estimator be correct for a fixed n? Here we've got one sample. And we're asking what happens as the size of that sample gets bigger and bigger and bigger and goes to infinity. And what you say is, this is called a p-lim. So what you say is if the probability limit of beta hat equals beta, then beta hat is consistent. All that means is that if you have an estimator, beta hat, and I let n go to infinity, as n gets bigger and bigger and bigger and bigger and bigger, I'll eventually hit the true value. So remember that we showed earlier that the expected value for rolling a dice is 3.5. 1/6 times 1 plus 1/6 times 2, blah, 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 plus 1/6 times 6. It's 3.5. On average, the value of the die will be 3.6. If I take a sample size of 10, I won't necessarily get 3.5. I might get 2 6s and 2 1s and a 2 and a 5 or something like that. Maybe I got lucky there to get 3.5. I don't think so. And so for a fixed sample size, I'm not necessarily going to get the right answer. If I repeatedly throw 10, write down the mean, throw 10, write down the mean, throw 10, write down the mean, then I average all those means, I'll get the true, I'll get mu. That's unbiasedness. It's the average value of a fixed sample size. On the other hand, I can think of consistency would be if I roll the dice an infinite number of times, the mean that I estimate as n gets bigger and bigger and bigger should get closer and closer and closer to the true value. Basically, for those of you who had math, I'm not going to ask you about this, but the technical thing is that the limit as n goes to infinity of the probability that the absolute value of beta minus beta hat is less than some delta is equal to 1 for all delta greater than 0. It just says as n gets bigger and bigger and bigger, I can make delta as small as I want. If I let n get large enough, the probability that I'm closer to the true value is going to be less than delta. That probability is 1. So it's just another way of saying that as n gets larger and larger and larger, we'll converge to the true value. Now, these probability limits work for distributions, not just estimators. So another way to think about consistency, and we've already talked about this a little bit, as n gets bigger and bigger and bigger, the t distribution converges to a normal. If I let n go to infinity, t is exactly equal to a normal. But what I just wrote would say, when n gets big enough, it gets arbitrarily close. And as we've said earlier, when n gets above 30, it's pretty dang close already. Okay, one last thing and then a couple of short notes. The law of large numbers. And the central limit theorem. Fancy names for, I think, a relatively easy concept, though. If you've ever had to prove this, it's a little challenging at times. So let beta hat n be an estimator of beta based on a random sample x1 to xn. So I'm just saying this estimator is based upon just n observations. So this could be the mean. Beta hat n could be x bar for n observations. And this would be mu, for instance. But this is true for, this could be the variance. It could be any estimator. Doesn't really matter. Okay. Let mu be the expected value of beta hat n, and sigma squared be the variance of beta hat n. Okay. Then beta hat n minus mu over sigma converges to a normal 0, 1 as n goes to infinity. Now, why this is an important result is this is true under really, really general conditions. There's some times when it's not true. There's a few distributions in the world that you could find that are special cases. Those aren't ever going to come up in the things we do, or you do in 421, or anything like that, so we don't need to worry about them. But what this is saying is it doesn't matter what the distribution of the x's. The x's could be uniform. They could be chi-square. They could be f. They could be t. They could be anything. They could be, there's other distributions. I won't get into gammas and betas and Maxwell's and all sorts of things, and Cauchy's. The Cauchy's kind of an exception. It doesn't have a mean. But anyway, there's all sorts of distribution. It doesn't matter what these are. This is always distributed normally. And so the best case of this is just x bar. So let x bar be an estimator of mu. We've got a sample of 100, n's 100. Mu is the expected value. Sigma squared x bar is the variance of x bar. And this is telling us that x bar minus mu over sigma x bar is distributed normally. So it doesn't matter what the distribution of these things are. We can start with these being distributed f. If we calculate the mean and we let n get big, it will be distributed normally. So anything involving, and it turns out that extends to just linear combinations of x's like a1, x1 plus a2, x2 plus a3, x3. This result's still going to hold. That's going to be important because it's going to tell us that if n gets big enough, any kind of estimator of that form, any kind of weighted mean or any mean, will converge to a normal. And that's going to be very, very helpful because that's going to allow us, when n gets big, to always rely upon a normal distribution and not have to worry about how these things are distributed. All right. There's two more topics that are covered in those first two chapters, and this would be in chapter 3. Testing hypotheses is one. And confidence intervals, remember those? Hopefully fondly, but I'm thinking it might not be. Those are two other topics that are covered in chapters 2 and 3. I'm going to save those for later on when we actually get to hypothesis testing for regression models. Because again, I don't want to have to say the same things over and over. It'll come out to be a lot of the same material. So I'll just save that until later. And so that ends chapters 2 and 3, at least the highlights that I covered. And we'll go on to bivariate regression, two-variable regression models in chapter 4 in the next video. Thank you.